Welcome back to Advanced Microeconomics and this third video on auction theory. In this video, we're going to look at first price sealed bid auctions. So let's recall the basic setup. There are n bidders who are bidding for some object for which they have value, and these values are private. So bidder I has a private value VI, okay? And what we're going to assume about these values is that they are independent, statistically, and that they're also identically distributed, but they're all uniformly distributed. So they are uniform on the interval 0 to 1 to keep things as simple as possible. Okay, so every bidder has some private value, and it's equally likely to be anywhere in this interval between 0 and 1. These bidders are risk neutral, expected utility maximizers, or if you like, expected value maximizers. And okay, so that's the setup. So what are the rules of the game? Well, each bidder submits a bid. So we submit bids. So maybe B1 up to Bn. Everybody submits some bid. And then the rules are very simple. The highest bid wins. And what does it mean to win? That means you get the object. Okay, so you get the object. And also you pay your bid. And hopefully you'll get some surplus there. You value the object more than your bid, you'll get some surplus. Okay? Now, if you don't win, then you don't pay. So no win, no pay. That sounds obvious, but in some auctions, that's not the case. Okay, so in some auctions, you might have to invest a lot just to get your bid in there, and it does involve paying whether you win or not. So in this case, no win, no pay. So everybody submits bids, the highest bid wins. The other thing is that the bids are simultaneous. So when I submit my bid, I have no idea what my opponents have bidded. We all bid at the same time. Or if you like, we could bid at different times, but we just put them in envelopes. So that's why we call it a sealed bid auction. Okay? So what are the payoffs going to look like? So the strategies, these bids are non-negative numbers, okay? So that's our choice of action. We choose any number that's non-negative, and we have some private value. And so our payoff I could write as pi we use for payoff. So the payoff, expected payoff from bidding a bid B when my value is V. I'm going to put this straight line as kind of conditional on my value V, in the sense that I take that as given. Okay, so I submit a bid B, my value is V. What's my expected payoff? Well, with some probability, which we'll analyze a lot more, with some probability I win the auction, in which case I get the object, which gives me value V, but I have to pay B. So V minus B is my profit or surplus, if you like. And then it's zero otherwise. Remember, no win, no pay. And so with probability 1 minus the probability of winning, I get 0. So it takes a very simple form, this expected payoff. Now, this is a game of incomplete information because we have private values. So the way we analyze this, essentially this is what's called we're going to look at what's called a Bayes-Nash equilibrium. Don't be too worried about that. The idea is we set this up using the following idea of bidding strategies, and then we look for a Nash equilibrium bidding strategy. So what does that mean? So a bidding strategy. Okay, you could think, well, I don't know this person's value, but I'm interested in the rule that they use in order to come up with their bid. Okay, so it would be a function. And I could write a value something like this, B as a function of VI. Okay, or I suppose I could write BI, so we could all have our own particular bidding functions. So I take my value VI, I plug it into my function bi, and then out pops a bid. Okay, so this would be a non-negative number. Okay, so this function describes, I don't need to know the person's value straight away. In a sense, I could just learn the rule that they use to turn whatever their value happens to be into a bid. And that's about the best we can do in this setup with incomplete information. These are private values. So what we'll be looking for is a Nash equilibrium bidding strategy, essentially. Now, we're going to make a simplifying assumption here, but it's a pretty reasonable one, which is to say that everybody uses the same bidding strategy. Okay, so all bidders in equilibrium use the same function B. Okay, now this does not mean they bid the same amount because they have different values. Okay, but if I'm player 1, I submit bid B V of 1, and player 2 will submit a bid B of V2, and so on. So we have different values, and so we're possibly submitting different bids, but this function, this B function, is the same. We're going to take that as the same for everybody. Okay? So in this sense, what we're looking for is what we would call a symmetric Nash equilibrium bidding function or bidding strategy. And we'll label that B star, okay? So notice that I didn't put a subscript on this B. I didn't put BI because we're all using the same strategy. Now, this seems quite reasonable, actually. All it means essentially is if two people have the same value, they do indeed bid the same amount. So it's not an unreasonable assumption. It can be shown to be the only equilibrium, but we're going to take it as given to simplify our analysis. Okay? So what we're looking for is a symmetric Nash equilibrium bidding strategy for this first price auction. Now, this has when I say a Nash equilibrium, we should remember that that has a very important property, which essentially means if a bidder, so I'll write this out, if bidder with value V believes all others use B star. Okay, so if this bidder, and he has a value V, believes that all other bidders are using the same B star function, and it's a symmetric Nash equilibrium bidding strategy, well then submitting then a bid B star of V is precisely what this bidder should do. So it maximizes expected payoff. Okay, so that's what we mean by a symmetric Nash equilibrium bidding strategy. And we want to figure out, well, what is the symmetric Nash equilibrium bidding strategy? Now, to simplify our analysis, so I'm going to make two simplifying assumptions. And hopefully these are pretty acceptable. Okay, so the first, I'm going to assume that this is a strictly increasing function. So B star is strictly increasing. What does that mean intuitively? People with higher bids, people with higher values submit higher bids. So that seems reasonable. People with higher values submit higher bids. People with lower values submit lower bids. It's a strictly increasing function. The second condition we're going to assume is that the person with value 0, B star of 0, submits a bid of 0. Why wouldn't they? Okay, so that seems pretty reasonable as well. Now, this first assumption, the fact that it's a strictly increasing function, turns out to have an important implication mathematically. Strictly increasing functions, you can invert them. Okay, there's a well-defined inverse function. So, so because of 1 implies that B star has a well-defined inverse function. And we're going to work with this. It turns out to be really useful to work with this inverse function. Let's call this function phi, which is B star to the minus 1. What does that mean? Okay, just to remember what that means, it means that for all B-V combinations, so for all bid value pairs, this function phi of B equals V if and only if B star of V equals B. Okay? So a person with value V in equilibrium, so they're plugging it into this equilibrium function B star, and out pops a bid B. Now, if we invert that expression, it's saying, how would we interpret this side? Is saying the person who bids B in equilibrium has value phi of B, which is value V. Okay? So how much does bidder who bids B in equilibrium value the object? That is phi of B. So it's the inverse function. And remember, this is the inverse of the equilibrium bidding function, not just any old function. It's the inverse of the equilibrium bidding function. Okay, so let's see why this is useful. If we go back to the expected payoffs in this game, okay, we're going to be able to say a bit more now about this expected payoff, which we know in equilibrium we are maximizing. So if we remember, it was my payoff when I bid B, given that my value is V, is the probability that I win times by V minus B. Okay? Now I've left this very kind of vague here. The probability that I win. What does that mean here? Can I do any better? Well, yes. So suppose, and remember we're talking about equilibrium, if this bidder believes all others use B star. Okay, so what does that mean? Let's imagine our bidder is player 1. So suppose bidders 2 all the way up to n. So everybody apart from player 1 uses B star. Okay? So what's the probability that player 1 wins the auction? Well, it's going to depend. So the probability of winning for player 1, it's going to depend on his own bid, but everybody else's bid is now fixed. So we could write this as some function. Let's write rho of B. It's a function of my bid alone, okay? How can we say a bit more than this? So what does this equal? This probability of winning, which is some function rho of B. Well, it would be the probability that my bid is better than player 2's bid, so B star of V2 is less than or equal to my bid B, okay? And these are independent, so I can multiply here, times the probability that player 2's bid is less than my bid, all the way up to, all the way up to player n. So the probability that B star V of n is less than or equal to my bid, okay? Now remember, this we can invert this B star, and we're assuming that this B star is an increasing function, so we can invert it. So this thing would equal, well, if player 2's bid is less than my bid, that means essentially that it's the same as saying the probability that V2, this player 2's value, is less than or equal to the value of someone who bids B, phi of B. Okay? So make sure that's fully understood, that idea. So that's exactly the same. And all the way up to player n, the probability that player n's value for the object is less than or equal to the value of somebody who bids B. Okay? Now we're talking about values. I know that values, if I go all the way back up to the top, values are uniform on 0, 1. Okay? So, these particular probabilities, using the uniform distribution that we've worked with quite a lot already, the probability, this term here, the probability that this uniform random variable is less than a specific number is just equal to that specific number. So this is phi of B times by itself. And how many are there? Players 2 all the way up to n. So there's n minus 1 of these. So this row of b, apologies, I said phi, didn't I? Row of b is equal to phi of b to the power n minus 1. Okay? And this is the probability of player 1. Remember, this is the probability that player 1 wins the auction when he submits a bid of b, given that every other player is using this symmetric Nash equilibrium bidding function. So I can now write his expected payoff. My payoff of player 1, if I bid b when my value is v, v1 I guess, would be this row of b, which I know what that looks like. It looks like this, times by v minus b. Okay? Now, remember, we're talking about a symmetric Nash equilibrium here. So this expression, this expected payoff, has to be maximized. When is it maximized? When I'm submitting a bid that is equal to what the symmetric Nash equilibrium would prescribe for my particular value. That's the definition of a Nash equilibrium bidding function. So this payoff would be maximized at that point. It turns out it's useful to rephrase this. This is equivalent to saying if my if phi of b is equal to v. Okay, that's exactly the same. What's the value of somebody who bids b? It's equal to in equilibrium is equal to v. Okay, so if I maximize this, if I know that this expected payoff is maximized when this is true. Okay. So what do we know about maxima? Well, we typically work with first order conditions, right? So the first order condition would say that the derivative is 0. So if I put a derivative is 0 when this thing is true. Okay, so if I differentiate this expected payoff, then I know that when I plug in phi of b equals v, it should equal 0 because that's where I'm maximizing my payoff. So what does the derivative of this particular payoff function look like? Well, notice that this expected payoff function involves a product. So it's useful to just rewrite it, just to go through the rules of calculus we're using, as row of b times by v minus row of b times by b. Okay, and you can see here that we have a product of two functions of the bidding b. Okay, so if I'm going to take the derivative here, the derivative of this evaluated at this point with respect to b would be, I take the derivative of the first term, so the derivative of row with respect to b times by the constant v minus, and then I have this product, so I take the derivative of the first term with respect to b and times it by the second term, and then add to that the first term, row of b, multiplied by the derivative of the second term, which is just the derivative of b with respect to itself, which is just 1. Okay, so this equals, can I express it? So the derivative of row with respect to b evaluated at b, and then I've got it being multiplied by v and minus b, so v minus b, and then deduct from that row evaluated at b. Okay, so this is the derivative of the expected payoff function with respect to b, and we know, we've argued above, that this should be 0 when this is true. Okay, so phi doesn't seem to appear in here just yet, but remember that this row function b is equal to phi of b to the power n minus 1. Okay, so I could rewrite this this derivative, just substituting that term as this derivative here would be So I've just used the chain rule there, multiplied by v minus b, minus this row of b here, which is phi of b to the power n minus 1. Okay, so this is the derivative, and it's 0 when v is equal to phi of b. Okay, so this is what we're going to replace, just this one term, just this v. We're going to replace it with phi of b. Let's do that. So what do we get? N minus 1 times by phi of b to the power n minus 2, the derivative of phi of b, multiplied by v, which is equal to phi of b when we're maximizing payoff, minus b, minus this phi of b to the power n minus 1 equals 0. Okay, so I can simplify this a bit. I've got n minus 2 copies of this here and n minus 1 over here, so I could cancel this out. So let's write that line. We get n minus 1 times by the derivative of phi with respect to b times, let's keep putting in the arguments here, multiplied by phi of b minus b minus phi of b, just one copy left because I've divided by n minus 2 copies, equals 0. Okay, so what we're left with here is a differential equation. Okay, now this is not a mathematics course, so I'm not going to go into depth about how to solve this. We're going to use a trick that makes this real easy. It's a differential equation. Essentially, what does it mean to solve a differential equation? Okay, what it means is to say that, well, this phi function of b is equal to something. Okay, we're looking for a function that has this particular property. Let's label it star. Now, we're not quite sure what the function is. So how could we go about finding it? Well, let's look at the most simple types of functions first and see if they work. And we're going to get lucky. So we're going to check, is the solution linear? That would be that would be lovely, right? And it turns out it is, it does work. So how do we check that it's linear? Essentially, we're going to assume it is linear, and then when we substitute it into this expression, as long as we don't get any contradiction, then we're good. We know we have a solution, okay? So what would it mean for phi to be linear? Phi of b would be equal to alpha times b plus some beta, right? Where alpha would be positive, because this is increasing, and beta could be any number, I guess. Well, it can't be any number, because remember our assumption. The person whose value is 0 in equilibrium bids 0. That was one of our assumptions. This means this is exactly the same as saying, this is equivalent to the person who bids 0 has value 0, right? That's just using the definition of phi. And that means that this beta would have to be 0, okay? So this implies beta must be 0 if the solution's linear, and so phi of b would have to be alpha times b for some alpha that's positive. And it's a constant, and that's what we're going to check. I'm going to substitute, so let's bring this equation down, this equation star, copy and paste. And what I'll do is I'll substitute this expression into this equation, and if we find that alpha is a positive constant, then we know we're good, okay? So that's how we go about solving this. So let's do that. We get n minus 1. This derivative term here would just be alpha, right? The derivative of alpha b with respect to b. Then alpha b minus alpha times b equals 0. And if we rearrange this, I won't go through all the steps because it's simple. What we would get is that this is equivalent to alpha equals n over n minus 1, which is a positive constant. So we're good. We've solved the differential equation. So phi of b equals alpha b. solves differential equation star. Excellent. Now, we haven't shown it's the only solution. It is the only solution, but we're not going to show that. But we're just happy that we've got a solution at this point. And we can be more specific here. This phi of b is n over n minus 1 times by b. Now, if we remember, this phi was the inverse of the Nash equilibrium bidding function. So this implies, or is equivalent to, our bidding function b star of v is the inverse of this expression, n minus 1 over n times by v. And there we have it. We've found the symmetric Nash equilibrium bidding function. It takes a very nice simple form. If I know anybody's value, I can plug it into this and it tells me what they should bid in equilibrium of this first price sealed bid auction. Okay, so let's have a quick look at its properties. So it's strictly increasing. I mean, we did assume that anyway, but it's nice that it's consistent with our assumptions, which means that the auction is efficient. What do I mean by that? The person with the highest value will have the highest bid, and so they win the auction. So the person with the highest value wins the auction, and that's what we mean when we say an auction is efficient. The person with the highest value wins. What about honest bidding? Well, notice that b star of v, this ratio here, this ratio n minus 1 over n, is less than 1. So this is less than v, right? And we call this bid shading. So when I know my value for an object, I'm not going to bid that. I'm going to bid less than my true value. So for example, if we have 20 players in the auction, my equilibrium bid would be to take my value, multiply it by 19 over 20, which is 0.95, my value. So I would bid only 95% of my value. You could say that I have shaded my bid by 5%. So that's a feature of first price sealed bid auctions in equilibrium. They're efficient, but people shade their bids. In the next video, we'll look at second price sealed bid auctions. So I look forward to seeing you there.